Right now, somewhere around the Pacific Ocean, a volcano is building energy. And when that energy is released, it won't ask for permission. 75% of the planet's active volcanoes are concentrated in one massive belt. The Pacific Ring of Fire. Some have destroyed entire cities. One cooled the planet. Another triggered tsunamis that killed tens of thousands of people, and millions lived directly in their shadow. The most dangerous part. Many of them look completely calm. So what truly makes a volcano deadly? The explosion? The lava? Or the number of people living too close? Today, you're going to understand how the most unstable region on Earth really works. And which volcanoes pose the greatest risk right now. Because it's not a question of if. It's a question of when. If you want to understand the warning signs before the planet decides to act, subscribe now, turn on notifications, and get ready to see Earth like never before. When people talk about dangerous volcanoes, the image that usually comes to mind is that of a mountain violently exploding, hurling lava and ash into the sky. But this image, although striking, does not even come close to explaining what truly makes a volcano a real threat to humanity. The danger of a volcano lies not only in the power of its eruption, but in a complex combination of geological, human, and temporal factors. There are extremely explosive volcanoes located in nearly uninhabited regions, whose impact on human life is minimal. At the same time, there are seemingly less violent volcanoes that pose a much greater risk simply because they are close to large urban centers. This means that the danger of a volcano cannot be measured solely by the size of the explosion but by the context in which it exists. One of the most critical factors is the type of magma. Volcanoes with more viscous, silica-rich magma tend to trap gases inside. As pressure builds up, the eruption becomes explosive, releasing energy in a sudden and devastating way. These are the types of volcanoes that produce ash columns reaching tens of kilometers into the atmosphere, pyroclastic flows capable of destroying everything in their path, and ash fall that can paralyze entire countries. Another essential element is eruption frequency. A volcano that is constantly active keeps populations on alert, but paradoxically may cause fewer casualties over time. Volcanoes that remain silent for decades or centuries, however, accumulate energy slowly and imperceptibly. When they finally awaken, they often surprise not only nearby populations, but even modern monitoring systems. History shows that many of the most dangerous volcanoes in the Ring of Fire were not considered immediate threats before major disasters occurred. Prolonged silence creates a false sense of security. Cities grow, roads are built, and entire generations pass without witnessing a single eruption. When the volcano awakens, it finds a completely different landscape from the one that existed during its last activity. Geographic location also plays a decisive role. Volcanoes near the ocean pose an additional risk, the potential to generate tsunamis. An explosive eruption, a partial collapse of the volcanic cone, or even a submarine landslide triggered by seismic activity can displace enormous volumes of water in seconds. In these cases, the impact extends far beyond the volcanic region and can reach distant coastlines. Another often overlooked aspect is invisible danger. Volcanic ash is not just dust. It is made up of microscopic fragments of rock and glass capable of damaging aircraft engines, contaminating water supplies, destroying crops, and causing serious respiratory problems. A volcano can cause global disruption without destroying a single city with lava. There is also the human factor. The higher the population density around a volcano, the greater the risk. Millions of people today live on the slopes of active volcanoes in the Ring of Fire. Some of these regions are highly monitored, others rely on precarious warning systems. In many cases, there is simply nowhere to run. In addition, the danger does not end when the eruption stops. Lahars, mudflows formed by the mixture of ash and rainwater, can rush down slopes for weeks or even months afterward, burying entire villages long after explosive activity has ceased. Many of the deaths associated with volcanoes do not occur during the eruption itself, but in the aftermath that follows. A dangerous volcano is also one that interacts with other natural systems. Eruptions can trigger earthquakes, landslides, and temporary climate changes. In some cases, major eruptions release so much material into the atmosphere that sunlight is partially blocked, altering temperatures and climate patterns on a regional or even global scale. Finally, perhaps the most unsettling factor is unpredictability. Despite all scientific advances, volcanoes remain extremely complex systems. They can give clear warning signs for months or change behavior within hours. The real danger lies in this combination of advanced science and permanent uncertainty. In the Pacific Ring of Fire, where dozens of tectonic plates interact, this complexity reaches its peak. It is there that the most monitored volcanoes on the planet are located, and also some of the most unpredictable. Understanding what makes a volcano dangerous is the first step toward understanding why this region concentrates so many of the Earth's greatest natural threats. And that is exactly what leads us to the next point: why the Ring of Fire hosts so many active volcanoes at the same time. If it were possible to observe the Earth from space and see only its internal activity, one shape would immediately stand out: a vast arc of fire and instability encircling almost the entire Pacific Ocean. This arc is not symbolic or metaphorical. It is real, measurable, and extremely active. It is what scientists call the Pacific Ring of Fire, the largest volcanic corridor on the planet. The name may suggest something continuous, like a perfect ring of flames, but reality is even more impressive. The Ring of Fire is made up of hundreds of active and potentially active volcanoes, distributed along more than 40,000 kilometers. It begins on the west coast of South America, moves up through Central America, runs along North America, crosses Alaska, descends through East Asia, passes Japan, the Philippines, Indonesia, Papua New Guinea, and reaches New Zealand. It is along this belt that about 75% of all active volcanoes on Earth are concentrated. But what truly makes this corridor unique is not just the number of volcanoes. It is the intensity, diversity, and frequency of their eruptions. Nowhere else on the planet are there so many different types of volcanoes: explosive, effusive, submarine, operating at the same time, all influenced by a single interconnected tectonic system. The Ring of Fire does not exist by chance. It is the direct result of the violent interaction between some of the largest tectonic plates on the planet. The Pacific Plate, the largest of them all, is surrounded by smaller plates that constantly push against it, sink beneath it, or slide laterally past it. This continuous movement creates ideal conditions for the formation of magma, pressure, and, eventually, volcanic eruptions. Unlike isolated volcanic regions such as Hawaii or Iceland, the Ring of Fire functions as a connected system. A major eruption in one location does not directly cause another in a distant area, but all of them respond to the same deep forces. It is as if the Earth's crust were permanently under tension around the Pacific. This tension manifests itself in different ways. In some places, volcanoes remain active for decades, with frequent small eruptions. In others, they remain silent for centuries before releasing a devastating accumulation of energy. This alternation between quiet and explosion is one of the most dangerous characteristics of the Ring of Fire. Another factor that makes this corridor so striking is its proximity to large human populations. Unlike in past eras, today millions of people live literally on top of this volcanic belt. Entire cities have been built near active volcanoes because volcanic soils are fertile, water is abundant, and the terrain favors human settlement. Risk has become normalized. Throughout history, the Ring of Fire has been the stage for some of the greatest eruptions ever recorded by humanity. Some destroyed entire cities, others altered the global climate, many occurred before scientific instruments even existed to measure them accurately. What we know today is only a fraction of what this system has produced over thousands of years. There is also an invisible aspect to this corridor. Much of its activity occurs beneath the ocean, in submarine volcanoes that are rarely seen, but that play a fundamental role in the planet's dynamics. These volcanoes create new portions of crust, reshape the ocean floor, and in some cases generate tsunamis capable of crossing entire oceans. The Ring of Fire is therefore far more than a collection of dangerous volcanoes. It is a geological scar that reveals where the Earth is constantly remaking itself. Where old crust is destroyed and new crust is born. Where the planet releases enough energy to reshape continents over time. That is why scientists consider this region one of the most important for the study of geology. Monitoring the Ring of Fire is not only a matter of human safety, but of deep understanding of how the planet works. Every eruption, every tremor, and every deformation of the ground are clues to processes occurring tens of kilometers beneath the surface. And the more we understand this volcanic corridor, the clearer it becomes that it is not an accident of nature. It is an inevitable consequence of a living planet, in constant motion. To understand why this corridor exists, and why it is so active, we need to go even deeper. Literally. We need to understand something that challenges our everyday perception: the surface of the Earth is not as solid as it seems. At first glance, it may seem like a coincidence. A vast ocean surrounded by active volcanoes in almost every direction. But what happens around the Pacific is far from random. In fact, this extreme concentration of volcanoes is a direct consequence of how the Earth dissipates its internal energy, and the Pacific is the main stage of this process. The interior of the planet is hot, far hotter than our intuition allows us to imagine. Even billions of years after its formation, the Earth continues to release heat constantly. That heat does not disappear. It needs pathways to escape. And one of those pathways is through the movement of tectonic plates. The Pacific Ocean occupies the largest ocean basin on the planet. The crust that forms its floor is predominantly oceanic, denser and heavier than continental crust. This creates a unique condition: along almost its entire perimeter, this oceanic crust is being pushed beneath continental plates or beneath other, less dense oceanic plates. This process is slow, silent, and inevitable. As the oceanic plate sinks, it descends into increasingly hotter regions of the Earth's mantle. There, pressure and temperature begin to alter the composition of the rocks. Minerals release water and other volatiles, lowering the melting point of the surrounding material. The result is the formation of magma. This magma, lighter than the solid rocks around it, tends to rise. It seeks fractures, faults, and zones of weakness in the crust. When it finds a path to the surface, a volcano is born. The Pacific is surrounded by exactly this type of tectonic boundary. Not one or two, but dozens of them, forming a true belt of subduction. Each of these zones is an active factory of magma. Each one feeds volcanoes that can remain active for thousands of years. That is why, unlike other regions of the world, the Ring of Fire does not depend on isolated points of activity. It is sustained by a continuous system. Where one plate sinks, another reacts. Where there is friction, there is energy. Where there is energy, there is volcanism. Another crucial factor is the constant movement of the Pacific Plate. It is not stationary. It moves at a rate of a few centimeters per year, which may seem insignificant, but on a geological timescale it is extremely fast. This movement keeps subduction zones active, continuously renewing the conditions for magma formation. In addition, the edge of the Pacific is not uniform. In some regions, plates collide almost head-on. In others, they slide at an angle. In certain areas, fragments of plates break, bend, or overlap. Each of these interactions generates a specific type of volcanic activity. That is why the volcanoes of the Ring of Fire are not all the same. Some produce fluid lava that flows slowly. Others generate violent explosions, with ash clouds and pyroclastic flows. This diversity of behavior is a direct result of the diversity of tectonic interactions. There is also the factor of time. The Pacific has been surrounded by subduction zones for tens of millions of years. This means the system has had enough time to become highly efficient. Old volcanoes collapse, new ones form, entire chains emerge and disappear. The cycle never stops. In contrast, other regions of the planet have different tectonic boundaries. Some have transform faults, where plates slide laterally without creating large-scale magma. Others are stable regions, where the crust is thick and resistant. The Pacific, by its very geometry, did not have this luxury. There is also a little noticed detail: the Pacific is slowly shrinking. As more oceanic crust is pushed into the interior of the planet than is created at its ridges, the Pacific basin decreases in size. This process further intensifies activity along its edges. Every centimeter of crust that disappears beneath the Pacific represents energy being redistributed. It represents magma being formed. It represents volcanic potential. That is why, when we observe a global map of active volcanoes, the pattern is so clear that it is almost unsettling. The Pacific is not merely surrounded by volcanoes. It is defined by them. The Ring of Fire is, essentially, the place where the Earth works most intensely to maintain its thermal and structural balance. It is there that the planet bends, recycles itself, and transforms before our eyes, even though, many times, we only notice this when the transformation becomes violent. And to understand why some of these volcanoes are far more dangerous than others, it is necessary to look at one of the central protagonists of this story, the Pacific Plate itself, the largest on the planet. Imagine two gigantic plates of the Earth's crust moving slowly, almost imperceptible to our senses, yet carrying forces capable of reshaping continents, creating mountain ranges, opening oceans, and generating some of the most violent volcanoes in the planet's history. It is within this invisible, deep, and continuous scenario that the true recipe for the most dangerous volcanoes of the Pacific Ring of Fire is formed. The key word here is subduction. A process that occurs silently, every day, beneath our feet, and that turns the Earth's interior into a kind of pressurized cauldron. Subduction occurs when a tectonic plate, usually oceanic and denser, slides beneath another plate, sinking slowly toward the Earth's mantle. In the Pacific Ring of Fire, this process is not the exception, it is the rule. The Pacific Plate, the largest on the planet, is surrounded by active subduction zones along virtually its entire edge. And it is exactly there that the chain of events begins that makes this region so explosive. When an oceanic plate dives beneath a continental plate or beneath another oceanic plate, it does not simply disappear. As it sinks, that plate carries with it water, marine sediments, minerals, and gas-rich materials trapped for millions of years on the ocean floor. This detail is crucial, because water, under high temperatures and extreme pressures, completely changes the behavior of deep rocks. As the subducting plate descends, temperatures increase drastically. The water contained within minerals begins to be released, infiltrating the upper mantle. This process lowers the melting point of mantle rocks, causing them to partially melt. This is how magma is born, not as a river of incandescent lava, but as a viscous, hot mixture that is extremely rich in gases. And here enters the second ingredient of this recipe, the type of magma. In volcanoes associated with subduction, magma tends to be thicker, more viscous, and richer in silica. Unlike basaltic magma, fluid and relatively predictable, found in volcanoes such as those in Hawaii. Magma from subduction zones behaves like a dense, sticky, and unstable mass. It does not flow easily. It accumulates pressure. This high viscosity prevents dissolved gases from escaping gradually. Water vapor, carbon dioxide, sulfur dioxide, and other gases become trapped within the magma, as if they were being compressed inside a geological pressure cooker. The more slowly the magma rises toward the crust, the greater the internal pressure that builds up. This is one of the reasons why volcanoes of the Ring of Fire do not erupt with constant and predictable frequency. They go through long periods of apparent dormancy, while pressure grows silently beneath the surface. When they finally find a fracture, a fault, or a point of weakness in the crust, the release of this energy is not gradual, it is violent. Pressure is the third fundamental element of this equation. Thermal pressure, chemical pressure, and mechanical pressure work together, stacking energy for decades, centuries, or even millennia. At depths of tens of kilometers, magma accumulates in magma chambers, slowly expanding, pushing against surrounding rocks, deforming the crust and generating almost imperceptible signals at the surface. Small earthquakes, millimetric ground deformation, changes in the composition of released gases. But the system is not static. Each new pulse of magma rising from the mantle adds more heat, more gases, and more volume to the magma chamber. The roof of this chamber, composed of solid rock, begins to behave like a fragile lid, subjected to increasing pressure. It is at this point that the system enters a critical state. Unlike volcanoes associated with hotspots, where magma finds more direct pathways to the surface, subduction volcanoes must fight against a thick, fragmented, and highly resistant crust. This difficulty further increases the accumulation of energy. The result is not gentle eruptions, but explosions capable of launching ash tens of kilometers into the atmosphere, generating devastating pyroclastic flows, and altering regional, or even global, climate. Another decisive factor is the interaction between rising magma and groundwater. In many regions of the Ring of Fire, deep aquifers come into contact with hot magma. When this happens, the water vaporizes instantly, expanding thousands of times in volume. This phenomenon, known as a phreatomagmatic eruption, adds even more violence to the eruptive event, fragmenting the magma into extremely fine particles and dramatically increasing the destructive power of the explosion. That is why so many volcanoes in this region produce enormous ash columns, capable of grounding air traffic, contaminating water sources, destroying crops, and affecting millions of people hundreds or thousands of kilometers away. Subduction creates the magma. The magma accumulates gases. Pressure turns all of this into a geological weapon. But there is an even more unsettling detail: this process does not occur at a single isolated point. It happens simultaneously in dozens of zones around the Pacific. From Japan to Chile, from Indonesia to Alaska, entire volcanic systems are connected by the same deep mechanism. Each volcano is a partial release valve of a system far larger, far older, and far more powerful than any structure built by humanity. This connection explains why volcanic activity in the Ring of Fire sometimes seems to occur in chains or sequences. A major earthquake can alter the stress balance in a subduction zone, influencing the behavior of nearby volcanoes. An eruption can relieve local pressure while increasing stress in adjacent regions. Everything is interconnected within a dynamic and extremely sensitive system. When we observe a volcano erupting in this region, we are witnessing only the final act of a process that began tens of kilometers beneath the surface, millions of years ago, with the slow and constant movement of tectonic plates. The spectacle of fire, ash, and lava is merely the visible manifestation of invisible forces that never cease. And it is precisely this combination, active subduction, viscous magma, and accumulated pressure, that turns the volcanoes of the Ring of Fire into the most violent on the planet. They do not erupt merely to release lava. They explode to relieve a system that has been compressed for generations. Understanding this recipe is not just a scientific matter. It is a matter of survival. Because as long as these plates continue to move, and they will, the Ring of Fire will remain one of the most unpredictable and dangerous regions on Earth. And now that we understand how this subterranean machine works, the next step is to look at real examples, specific volcanoes that showed the world what happens when this recipe reaches its maximum point. At the beginning of 1980, Mount St. Helens was just another snow-covered volcano in the green landscape of Washington state, in the United States. To many, it appeared dormant, almost forgotten. Trails, dense forests, and tranquil lakes occupied its slopes, frequented by tourists, loggers, and local residents. But beneath that serene appearance, something was beginning to change, silently. Mount St. Helens is part of the Cascade Range, a chain of volcanoes directly associated with the subduction of the Juan de Fuca plate beneath the North American plate. In other words, it was embedded in exactly the same geological machinery that feeds the most violent volcanoes of the Pacific Ring of Fire. The problem was that, at the time, both the public and part of the authorities still underestimated how quickly this system could spiral out of control. It all began with small earthquakes. In March 1980, shallow and repetitive seismic events started to shake the region around the volcano. At first, they seemed insignificant, tremors that merely rattled windows and caught the attention of seismographs. But to more attentive geologists, this was a classic sign of magma in motion, slowly rising through the crust. Days later, the volcano began releasing steam and ash. A fissure opened at the summit, forming a growing crater. Mount St. Helens was awakening after more than a century of relative dormancy. Scientists from the United States Geological Survey began monitoring the mountain full-time. Instruments detected something alarming: the volcano's northern flank was swelling. This swelling was not symbolic. The mountain was literally deforming. In some places, the slope was moving outward by more than 1 meter per day. It was as if something gigantic were being pushed from the inside out, pressing the structure of the volcano to its limit. The magma could not rise vertically, so it began pushing sideways, creating a massive and unstable bulge. This detail is crucial to understanding what came next. Unlike most eruptions, which occur through the top of the volcano, Mount St. Helens was preparing for something far rarer and more dangerous: a lateral eruption. Some scientists warned of this risk, but the concept was still poorly understood outside academic circles. Nothing of that magnitude had ever occurred in the modern continental United States. Meanwhile, political and economic pressure grew. The region around the volcano was important to the logging industry, and many landowners pushed to reduce exclusion zones. Some areas were reopened, despite increasingly clear signs of instability. The volcano was giving warnings, but they were not fully taken seriously. On the morning of May 18, 1980, at 8:32 a.m., a magnitude 5.1 earthquake struck directly beneath Mount St. Helens. This tremor was the final trigger. The northern flank, already weakened by continuous swelling, simply collapsed. The largest landslide ever recorded in history occurred in seconds. But the collapse was only the beginning. With the sudden removal of the natural lid that had been holding back pressurized magma, the volcano instantly released its accumulated energy. The result was a devastating lateral blast, traveling at over 480 kilometers per hour. In less than 3 minutes, an area larger than an entire city was completely destroyed. Forests were flattened like matchsticks. Centuries-old trees were ripped from the ground and hurled kilometers away. Rocks, ash, and superheated gases formed a deadly cloud that advanced without giving any chance of escape. People dozens of kilometers away reported intense heat and a deafening roar, as if the sky itself were tearing apart. 57 people died that day. Among them was volcanologist David A. Johnston, who was monitoring the volcano from a post considered safe. His final radio transmission was brief and chilling: "Vancouver, Vancouver, this is it." The eruption sent ash more than 24 kilometers into the atmosphere. Day turned into night in distant cities. Ash covered roads, destroyed crops, and caused billions of dollars in economic damage. Rivers were blocked by debris, triggering secondary floods that prolonged the disaster for weeks. But the impact of Mount St. Helens was not only physical, it was scientific and psychological. For the first time, the modern world witnessed in real time the full power of a subduction volcano in active eruption. All the elements discussed in the previous topic were present: viscous, gas-rich magma, pressure accumulated over decades, and an abrupt release of energy. Mount St. Helens became a turning point in volcanology. After the eruption, monitoring protocols were completely reformed. The use of GPS to measure ground deformation became standard. Gas analysis gained critical importance. And, above all, it became clear that volcanoes do not need to erupt vertically to be lethal. Another unsettling aspect is that Mount St. Helens did not stop in 1980. It remained active for years, with smaller eruptions, slowly growing lava domes, and new episodes of instability. This reinforced an essential lesson: a major eruption does not solve a volcano. It is only one chapter in a much longer story. Today, Mount St. Helens is one of the most closely monitored volcanoes on the planet. Sensors, cameras, satellites, and seismic networks track every breath of the mountain. But the warning it left goes far beyond its own slopes. It showed that the signs were there. The swelling, the earthquakes, the steam, the fissures, everything indicated that something extreme was approaching. What failed was not science, but risk interpretation, communication, and, in part, the human decision to underestimate invisible geological forces. Within the Pacific Ring of Fire, there are dozens of volcanoes in similar situations today. Some located near major cities. Others seemingly calm, yet slowly accumulating pressure. Mount St. Helens was not an isolated event, it was a warning. A brutal reminder that the Earth does not need much to drastically change landscapes, climate, and human life in a matter of minutes. And if a single volcano was capable of causing all of this, what happens when an eruption reaches an even greater scale? That is exactly what leads us to the next chapter of this journey. In June 1991, while the world was focused on political transformations, technological advances, and human conflicts, something far greater was unfolding quietly in the Philippines. In the center of Luzon Island, covered by dense tropical vegetation and largely forgotten by most of the global population, Mount Pinatubo was preparing to unleash one of the most impactful eruptions of the 20th century, not only for its region, but for the entire planet. Until that moment, Pinatubo was considered a relatively unremarkable volcano. Its last major eruption had occurred more than 500 years earlier. The mountain did not have the classic profile of a threatening volcano. There was no perfectly defined cone, nor visible rivers of lava. For many local residents, it was simply part of the landscape. For science, a potentially active volcano, but poorly understood. What no one imagined was that beneath that modest appearance lay one of the most dangerous magmatic systems ever recorded. Pinatubo is located exactly above an active subduction zone, where the Eurasian plate interacts with oceanic microplates along the edge of the Pacific Ring of Fire. There, for centuries, silica-rich, gas-laden magma had been slowly accumulating in large underground chambers. Unlike volcanoes that erupt with some regularity, Pinatubo had been storing energy for generations. In early 1991, the first signs appeared. Small earthquakes began to multiply beneath the mountain. Soon after, emissions of steam and gases started escaping through fissures in the ground. Analyses revealed something alarming: large quantities of sulfur dioxide were being released, a clear indication that fresh magma was approaching the surface. This time, however, something was different. Unlike many previous events in the history of volcanology, the warnings were taken extremely seriously. Filipino scientists, in partnership with the United States Geological Survey, quickly installed monitoring equipment around the volcano. Seismographs, gas sensors, and ground deformation measurements began to reveal an alarming picture: the system was entering a critical state. The magma was rising. The pressure was reaching critical levels. And time was running out. In the weeks leading up to the main eruption, Pinatubo began producing smaller explosions, releasing ash and rock fragments. To an untrained observer, this might have seemed like the peak of the event. But to scientists, these explosions were merely temporary valves, signs that something far greater was about to happen. Based on the data, a historic decision was made: to evacuate tens of thousands of people, including entire communities and a large American military base installed in the region. It was a massive, complex operation, and to some, it seemed excessive. But what followed would prove that this decision saved countless lives. On June 15, 1991, Mount Pinatubo entered full eruption. The explosion was colossal. Within hours, a column of ash, gases, and volcanic fragments reached more than 35 kilometers in altitude, piercing the stratosphere. The volume of material expelled was so immense that the top of the volcano simply collapsed, forming a caldera more than 2.5 kilometers in diameter. Pyroclastic flows, deadly clouds of superheated gases and debris, raced down the slopes at extreme speeds, destroying everything in their path. Even areas that had already been evacuated were completely buried. Rivers were filled with volcanic mud, creating lahars that continued to devastate villages for months after the main eruption. But the most remarkable effect of Pinatubo did not occur only on the ground. The eruption released approximately 20 million tons of sulfur dioxide into the atmosphere. This gas spread globally, forming a thin layer of sulfate aerosols in the stratosphere. This layer began reflecting part of the sun's radiation back into space. The result was something extremely rare in modern history: the planet cooled. In the months that followed, the average global temperature dropped by about 0.5 degrees Celsius. It may seem small, but in climatic terms, this value is enormous. Rainfall patterns were altered. Winters became harsher in some regions. The global climate cycle felt the impact of a single volcano. Pinatubo became definitive proof that volcanic eruptions are not merely local events, they can directly interfere with Earth's climatic balance. For the first time, modern science was able to observe, measure, and confirm this effect on a planetary scale. Another crucial aspect was the validation of climate models. Data collected after the eruption helped scientists better understand how atmospheric particles influence climate, providing essential information for studies on climate change and even geoengineering. Yet despite all this magnitude, the number of direct victims was relatively low, especially when compared to smaller historical eruptions. This was due almost entirely to effective monitoring and early evacuations. Pinatubo became a rare example of success in managing an extreme natural disaster. Even so, the social and economic impact was immense. Indigenous communities lost ancestral lands. Infrastructure was destroyed. The landscape was irreversibly transformed. The volcano did not merely erupt, it reshaped the region. Today, Mount Pinatubo holds a lake within its caldera, seemingly calm. But this silence is deceptive. The volcanic system remains active. Pressure can build again. History, as the Ring of Fire itself teaches us, never truly ends, it only pauses. Pinatubo showed the world something few fully understood: Earth possesses natural mechanisms capable of altering the global climate in a matter of days. No human technology, no political boundary, and no economic system stands above these forces. And if a single volcano was capable of cooling the entire planet, what happens when destruction does not come from an isolated point, but from a chain reaction? In August 1883, the world had no satellites, global sensors, or modern warning systems. News traveled slowly, crossing oceans by ships and telegraph cables. Even so, one event was so colossal that its effects were felt, seen, and heard across nearly the entire planet. That event originated in a small group of islands in the Sunda Strait, between Java and Sumatra, at the heart of the Pacific Ring of Fire. Its name was Krakatoa. Krakatoa was not a single volcano, but a volcanic complex formed by several islands. For centuries, it remained relatively discreet, with moderate eruptions that rarely drew attention beyond the region. But, as in the case of Pinatubo, this apparent calm concealed a deeply unstable system, fueled by active subduction and magma extremely rich in gases. There, the Indo-Australian plate plunges beneath the Eurasian plate. The result is a perfect environment for the formation of viscous, pressurized, and explosive magma. For decades, perhaps centuries, Krakatoa had been silently accumulating energy. In May 1883, the first signs appeared. Smaller explosions began to occur, sending ash and steam into the sky. Ships passing through the region reported thunderous sounds coming from the island, columns of smoke, and incandescent rocks falling into the sea. Activity was increasing, but no one imagined that this was merely the prelude to one of the greatest explosions ever recorded in human history. On the morning of August 27, 1883, Krakatoa collapsed. What happened in the following hours redefined the concept of natural destruction. Four gigantic explosions occurred in sequence. The largest of them was so powerful that the sound of the blast was heard more than 4,800 kilometers away, becoming the loudest noise ever recorded in history. In some regions, people believed cannons had been fired. In others, they thought the end of the world had arrived. The energy released was equivalent to tens of thousands of nuclear bombs. The atmospheric pressure wave generated by the explosion circled the planet several times, recorded by barometers on different continents for days on end. But the true horror of Krakatoa did not come only from the sky. A large portion of the volcano simply disappeared. The explosion was so violent that it destroyed the structure of the island, causing it to collapse into the ocean. This collapse displaced enormous volumes of water, generating gigantic tsunamis. Waves more than 30 meters high struck the coasts of Java and Sumatra within minutes. Coastal cities were wiped off the map. Entire villages vanished without leaving a trace. It is estimated that more than 36,000 people died, most of them victims of the tsunamis, not the eruption itself. This is one of the most important aspects of Krakatoa. It showed that the impact of a volcano can multiply in a chain reaction. An eruption triggers a collapse. The collapse generates tsunamis. The tsunamis amplify the destruction on a scale far greater than the volcano itself. But the effects did not stop there. Ash and aerosols were injected to extreme altitudes, spreading throughout the global atmosphere. For months, and even years, the sky displayed strange colors. Intense red sunsets were recorded in paintings, reports, and diaries around the world. Global temperatures dropped slightly, and climate patterns were temporarily altered. People who had never heard of Krakatoa felt its effects without knowing their origin. The volcano had become a planetary event. Decades later, something even more unsettling happened. At the site where the original Krakatoa was destroyed, a new volcano began to emerge from the sea. It was named Anak Krakatau, the child of Krakatoa. Throughout the 20th century and into the early 21st century, Anak Krakatau grew slowly, building itself layer by layer, eruption after eruption. To many, it seemed like a smaller and less threatening version of its predecessor. But in December 2018, history showed that the cycle of destruction had not ended. A significant portion of Anak Krakatau's flanks suddenly collapsed into the ocean following an eruption. This submarine landslide generated an unexpected tsunami that once again struck the coasts of Java and Sumatra. More than 400 people died. The most frightening part, there was no major earthquake to serve as a warning. The tsunami arrived with almost no notice. This modern event reinforced a lesson left by the original Krakatoa: volcanoes can generate indirect catastrophes as deadly as the eruption itself. Structural collapses, submarine landslides, and water displacement can occur silently, rapidly, and with devastating consequences. Krakatoa became the ultimate symbol of the geological domino effect. A single instability can trigger multiple disasters, at different scales and speeds. And in the Pacific Ring of Fire, where many volcanoes are located near the ocean, this risk is constant. Today, Anak Krakatau is monitored 24 hours a day. But the system that feeds it remains active. Subduction has not stopped. Magma continues to rise. Pressure continues to build. The difference is that now we know, or should know, what is at stake. Krakatoa taught the world that Earth does not release its energy in isolation. It acts through interconnected systems, capable of transforming a local eruption into a regional or even global disaster. And if a volcano was capable of causing this level of destruction more than a century ago, what happens when it is located in one of the most densely populated regions on the planet? The question seems simple, almost straightforward. But behind it lies one of the greatest frontiers of human knowledge about the planet we live on. Can we predict a major volcanic eruption? The short answer is, not yet with absolute precision. The real answer is far more complex, and fascinating. Contrary to what many imagine, volcanoes rarely erupt without warning. The problem is not the absence of signals, but the difficulty of correctly interpreting what those signals actually mean. The Earth speaks all the time. The challenge for science is understanding when it is merely adjusting, and when it is about to explode. Before a major eruption, a volcano usually goes through a process of awakening. Magma begins to move at depth. Gases accumulate. Internal pressures increase. Rocks fracture. All of this generates detectable signals, but not always obvious ones. The first of these signals is usually an increase in local seismic activity. Small earthquakes begin to occur beneath the volcano, often imperceptible to the population. These tremors are not caused by moving tectonic plates, but by magma forcing its way through the crust. Each fracture generates a vibration. For scientists, this is like hearing footsteps coming from inside the mountain. But here lies the first major challenge: not every seismic swarm leads to an eruption. In many cases, magma rises, encounters resistance, cools, or redistributes without ever reaching the surface. If every tremor were treated as a harbinger of disaster, entire cities would live in a constant state of evacuation. Another important signal is ground deformation. As magma accumulates in underground chambers, the land around the volcano may slowly inflate, like a lung filling with air. Today, satellites can detect movements of just a few millimeters on the Earth's surface. Mountains that appear solid may, in reality, be silently expanding. This type of monitoring has already enabled successful forecasts. In several cases, satellite-detected deformation preceded eruptions by weeks or months. But again, the difficulty lies in interpretation. How much swelling is too much? At what point does internal pressure cease to be stable and become critical? The gases released by a volcano also tell an essential story. Sulfur dioxide, carbon dioxide, and water vapor escape through fissures and fumaroles long before an eruption. Sudden changes in the quantity or composition of these gases can indicate that magma is approaching the surface. However, this method also has pitfalls. Winds, rainfall, temperature changes, and even vegetation can affect measurements. In addition, some volcanoes release large amounts of gas continuously, even when they are not close to erupting. And then we reach the most delicate point of all, the unpredictable behavior of magma. Magma is not a simple liquid. It can be thick or fluid, hot or relatively cool, rich or poor in gases. Two volcanoes with similar appearances can react in completely different ways to the same internal stimuli. One may release pressure gradually through small eruptions. Another may seal its own outlet and explode catastrophically. That is why, to this day, there is no universal, volcanic clock. Each volcano must be studied individually, taking into account its history, composition, internal structure, and even its surrounding environment. Cases like Mount Pinatubo in 1991 show the best possible scenario. Scientists identified clear warning signs, authorities acted, evacuations were carried out, and thousands of lives were saved. In other cases, such as Nevado del Ruiz in Colombia, warning signs were detected but underestimated, and the result was one of the greatest volcanic tragedies of the 20th century. These episodes reveal an uncomfortable truth: prediction alone is not enough. Forecasts must be understood, communicated, and taken seriously. Today, science works with probabilities, not certainties. Alerts are gradual. Risk levels rise and fall. Evacuations must balance safety with social and economic impact. Removing thousands of people from their homes when an eruption does not occur can generate future distrust, and that, paradoxically, can cost lives when the danger is real. In the Pacific Ring of Fire, where dozens of active volcanoes coexist with large urban centers, this dilemma is constant. Japan, Indonesia, the Philippines, Mexico, Chile, all live with science walking side by side with uncertainty. And there is a physical limit we have not yet overcome: we cannot directly see the deep interior of the Earth. Everything we know comes from seismic waves, indirect measurements, computational models, and historical comparisons. It is like trying to understand a gigantic machine by listening to its noises through a wall. Even so, progress is remarkable. Global sensor networks, artificial intelligence applied to seismic analysis, increasingly precise satellites, and three-dimensional models of magma chambers are making predictions more reliable than ever. But the final truth remains: a major eruption never announces its date with absolute clarity. It approaches in silence, leaves clues, tests limits, and only then decides whether it will break through the surface or retreat once more into the depths. How prepared is humanity for an extreme volcanic event, when the warning arrives, or when it simply does not arrive in time? Humanity has always believed that technological progress would gradually make us immune to nature's greatest risks. We have built taller cities, instant communication systems, satellites that observe every centimeter of the planet, and mathematical models capable of simulating complex scenarios. But when it comes to an extreme volcanic event, especially within the Pacific Ring of Fire, the question is not whether we are advanced, but whether we are truly prepared. The honest answer is uncomfortable. In some ways, we have never been more ready. In others, we remain just as vulnerable as ancient civilizations that watched fire emerge from the mountain without understanding its meaning. Today, we are able to monitor volcanoes 24 hours a day. Seismic networks capture nearly imperceptible microtremors. Satellites measure ground deformation with millimeter precision. Chemical analyses reveal changes in the gases released by fumaroles. In theory, this set of tools should give us enough advantage to anticipate any major disaster. But reality is more complex. The first major obstacle is population concentration. Never before have so many people lived so close to active volcanoes. Fertile regions, rich soils, access to water, and historic trade routes have caused entire cities to grow around unstable mountains. Today, tens of millions of people live within zones of direct risk in the Ring of Fire. Cities such as Naples, Manila, Mexico City, Jakarta, Tokyo, and countless others are not exceptions, they are the rule. Removing entire populations from these areas is not socially, economically, or politically viable. This means that the strategy is not to avoid risk, but to live with it. And living with a volcano demands difficult decisions. When an alert level rises, evacuating too early can generate panic, massive economic losses, and a loss of trust in authorities. Evacuating too late can cost thousands of lives. This line is so thin that, often, one only knows whether the decision was correct after everything is over. Another critical problem is global inequality. While wealthy countries rely on cutting-edge technology, large scientific teams, and well-structured evacuation plans, many regions of the Ring of Fire are located in developing countries, where basic resources for continuous monitoring are lacking. In some places, an active volcano is observed by only a few outdated sensors, or by none at all. In others, communities do not even receive clear information about what a volcanic alert actually means. The risk is not only geological, it is social. Even where science is present, there is a factor that cannot be fully controlled: human behavior. History repeats itself. People who refuse to leave their homes. Others who return too early to protect material possessions. Communities that ignore alerts because they have experienced false alarms in the past. Collective memory is short, and routine tends to overcome fear. Moreover, extreme events do not affect only the area around the volcano. A major eruption in the Ring of Fire can disrupt international air routes, contaminate water reservoirs, affect crops, trigger economic crises, and even influence the global climate. The modern world is too interconnected for a disaster to remain local. Another sensitive point is response time. In slow eruptions, there may be days or weeks to act. But in sudden collapses, explosive eruptions, or volcanic tsunamis, time is measured in minutes. No evacuation plan is perfect when nature decides to act without clear warning. And then there is the scenario that worries scientists the most: events beyond the scale of recent historical records. Most emergency plans are based on data from the last few centuries. But the Earth operates on timescales of thousands and millions of years. There is no guarantee that the next major event will follow recent patterns. This does not mean that humanity is defenseless. On the contrary. We have never had so much knowledge, international cooperation, and rapid response capability. But we have also never been so exposed, so concentrated, and so dependent on fragile systems. In the end, human preparedness for an extreme event is not just a matter of science or technology. It is a matter of collective choices, where we build, how we educate, how much we trust science, and whether we are willing to act before danger becomes too visible. The Ring of Fire is not an enemy. It is a constant reminder that we inhabit a living planet, and that living here requires respect, vigilance, and humility. And this brings us to an even more unsettling question, which will be the next step of our journey. What if the extreme event is not just an ordinary volcano? What if a supervolcano decides to awaken within the Ring of Fire? When we observe the volcanoes of the Pacific Ring of Fire, it is tempting to see them only as threats. Unstable mountains, unpredictable explosions, forces capable of putting entire cities at risk. But this is only the surface of a much deeper story. Because, in truth, volcanoes are not a flaw of the planet. They are an essential part of how it works, and perhaps the key to understanding Earth's future. The Ring of Fire reveals, first and foremost, that our planet is not a static body. Earth is alive in a geological sense. It moves, it recycles, it transforms itself. Tectonic plates never stop. The mantle continues to transfer heat. The crust is constantly renewed. Volcanoes exist because the planet needs to release energy. Without them, Earth would have become a dead world billions of years ago. It is precisely because of volcanism that the atmosphere formed, that oceans emerged, and that elements essential to life reached the surface. Iron, sulfur, carbon, phosphorus, all of these fundamental components were brought up from the depths by volcanic processes throughout the planet's history. In other words, the same force that destroys also creates. When we look toward the future, the volcanoes of the Ring of Fire teach us an uncomfortable lesson: humanity does not control Earth, it merely inhabits its surface temporarily. We build cities, borders, and economic systems as if they were permanent. But from a geological perspective, all of this is fragile, fleeting, and provisional. Volcanoes do not wake up to attack us. They follow cycles far greater than our civilizations. A city may exist for 1,000 years. A volcano can remain active for hundreds of thousands. This difference in scale is what places us at a constant disadvantage. Earth's future, seen through the lens of the Ring of Fire, is not a future of absolute stability. It is a future of continuous transformation. Regions will change. Coastlines may disappear. Islands may emerge. Mountains may collapse. The planet will continue on its path regardless of our expectations. But this does not mean that humanity's future is bleak or doomed. On the contrary. What volcanoes truly reveal is the importance of knowledge, adaptation, and humility. Never before have we known so much about Earth's internal processes. Never before have we had such capacity to monitor, anticipate, and respond. Science does not eliminate risk, but it transforms surprise into preparedness. At the same time, volcanoes remind us that there is a clear limit to the illusion of control. We cannot stop an eruption. We cannot shut down a tectonic system. The most we can do is respect the signals, listen to science, and make decisions before it is too late. The Ring of Fire also exposes a central dilemma for humanity's future: how to coexist with an active planet without trying to dominate it. Will we continue building in high-risk zones? Will we keep ignoring warnings for economic convenience? Or will we learn to plan based on geological reality, rather than immediate necessity? There is one final revelation: perhaps the deepest of all. Volcanoes show us that Earth's future does not revolve around humanity. The planet has already survived mass extinctions, asteroid impacts, ice ages, and super eruptions. It will remain here, with or without us. The real question is not whether Earth will survive, but how we choose to live upon it. The ring of fire is not just a ring of destruction. It is a mirror. A reminder that we are part of something far greater, far older, and infinitely more powerful than any civilization. And perhaps the greatest mystery is not beneath the volcanoes, but in how we will learn to coexist with them in the future. If this journey changed the way you see the planet, if you now look at Earth not as a backdrop, but as a living organism, then this exploration was worth it.